In this example, we're going to be making use of the rational roots theorem, Descartes' rule of signs, and the boundedness theorem, all to help us factor this polynomial right here. 3x to the fourth plus 6x cubed minus 78x squared plus 54x minus 945. Now, first of all, the rational roots theorem tells us that we take all the factors of the last number, call it p, and do all the possible ways to divide that over all the factors of our front number, q. Now, of course, looking at this, I've got 945 and 3, and so that would be a pretty large list. And so it would be very helpful if I notice that everything here is divisible by 3, and I can take that out. If you don't do that, theoretically you could get the same answer, but you'd have to do a lot more work because you've got numbers in there that basically just waste your time because you know they're not going to work out. So I'll pull out this 3, and I'll be left with x to the fourth plus 2x cubed minus 78 divided by 3 comes out to be 26 plus 18x. And then 945 comes out to be, when I divide it by 3, 315. Okay, so there's my polynomial. Now, I could just try random things and divide, but I want to try to get some guidance as to what numbers to use, because there are an infinite number of numbers. So, first of all, rational roots theorem, I'll take all the factors of 315 and put them over all the factors of, well, 1. So that's pretty nice. P over Q is really just going to wind up being all the factors of P. So I'm going to have both positive and negatives for everything. So I'll just start listing with negatives. So I'm going to have negative 315. I'm going to have my calculator help me out here. So I suspect that that's divisible by 3, which it is. Let's see, what else are you divisible by? You're divisible by 35, so I'll list that. The order doesn't matter. I just want to have some sort of pattern there. Let's see. It's divisible by negative 15 as well. And 21. So see, it's a little out of order. That's okay. Let's see here. Negative 9, negative 7, negative 5, negative 3. Yeah, there might be a few more, but I'll go ahead and pause there. We'll get them if we need them. And then, of course, I'm going to have the positive versions of all this as well. Oh, and 1. So I'll go ahead and list that here. So I'll have 1, 3, 5, 7, 9. I'll put these in order. 15, 21, 35, 315. And again, there might be some zeros there that I missed. But since I'm going to be using the boundedness theorem in a moment here to help me out, I won't worry about that yet. Okay, so there's some of my factors. I won't say they're all there, but there's a lot of them. And you look at that and you go, okay, so rational roots theorem tells me that this list, whatever zeros are in my polynomial, are in this list. So if I just start going through, eventually I'll find one of the zeros. Okay, usually helpful, but because there's so many numbers here, I'm going to make use of something else called the boundedness theorem. And what the boundedness theorem tells me is that if I take a root and I do synthetic division, regardless of whether or not that works, of course, if it works, if I get a remainder of 0, then woohoo, I found a factor. But if it doesn't work, I can get useful information from it. If I divide by a negative number into my polynomial and I get alternating signs, that's going to tell me that there is no 0 less than that number. And so I can just ignore anything smaller than it. So I'm going to pick negative 9. I'm going to try division by negative 9 into this polynomial. And if I get alternating signs, I know I'm going to just be able to ignore all the numbers smaller than that. So let's try it. I'm going to look at my polynomial inside of here without the 3. So I'll have 1, 2, negative 26, 18, and negative 315. Another note is that I don't care that much what the numbers are. I care what the signs are. So I'll be using my calculator to get the numbers, but however big or small they happen to be, that's not really what I'm focused on. I'm just focused on, are the signs alternating? So 1, 2, negative 18. Okay, cool. So let's bring down 1. 1 times negative 9 is negative 9. Add the 2, I get negative 7. Negative 7 times negative 9 is going to give me a 63. 63 minus 26 gives me a 37. Multiply that by the negative 9. I get a negative 333. Add 18 to that, I get negative 315. Finally multiply that by negative 9. I get 2,835. Subtract 315. Oops. I get 2,520. But what I'm concerned with is positive to negative, cool. Negative to positive, cool. Positive to negative, Negative to positive, awesome. So since these signs alternate, notice this isn't a factor because I didn't get a remainder of 0. But I know that there's no number smaller than negative 9. So what I can do is I can just go through and cross out anything smaller than negative 9. Now remember, with negative numbers, smaller means like more negative. So negative 315 is out, negative 35, negative 15, negative 21. And since this remainder wasn't 0, I know negative 9 is out as well. I'll kind of circle it to remind me that that's my lower bound. No number smaller than that. Cool. Now I use negative 9. Let's use positive 9 to get my upper bound. So for getting an upper bound, you divide by a positive 0. And the way that one works is if all the numbers down here are non-negative, in other words, 0 or positive, then this will be my upper bound. No 0 will be bigger than this guy. So let's get to it. Same numbers, 1, 2, negative 26, 18, negative 315. Okay. Bring down the 1. 1 times 9 is 9. Add that, I get 11. 9 times 11 is 99. Subtract 26. I'm going to get 73. 73 times 9 is 657. Add that to 18, I get 675. Multiplied by 9, I get a ridiculously large number, 6,075. And subtract 315. So I get this. Again, my main concern is that those are all positive. They're all non-negative. Got positive, 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 positive. So that's my upper bound. That tells me that no 0 is going to be larger than 9. So out goes this, 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 this. And since I didn't get a remainder of 0, I can remove 9 as well, who I'll circle because that's my upper bound. Now I just want to emphasize there's not really a reason behind picking 9. I just was hoping that I would get a somewhat smaller bound. And so I didn't start out here at 315 because I already know that that's my smallest possible number. And I already know that 15 is my largest. Then it was just sort of a gamble of how close I want to come in to get these numbers nice and small. But it worked out. So now my new list is really just negative 7, negative 5, negative 3, negative 1, and then the positives, 1, 3, 5, 7. That's it. That's my list of zeros. So that's how the boundedness theorem can be very helpful. P over Q gives you a list, but if that list is huge, you might want to try to get it as small as possible before you just start trying random numbers. Of course, if you try random numbers, you can look at what you get and make conclusions from there. So let me make myself some room here, because now I'm just going to try to factor this. And actually, before trying to factor, I can make use of Descartes' rule of signs to give me an idea of whether or not I want to try out positive or negative numbers or anything. Maybe there's one where I'm guaranteed to get a result, and maybe I don't have any types of some other zeros. So, again, let me make some room here. I'll show you what I mean. Okay, so what Descartes' rule of sign tells you is you look at your original polynomial and you count the number of sign changes. So if I do that as is, positive to positive, that's no change. Positive to negative, that's one sign change. Negative to positive, that's another. Positive to negative, that's another. So my possible number of positive zeros is going to be that amount that I counted, so there's 3, or it could be less, and it would go down by 2s every time. So I'd go down to maybe there's 3 positive real zeros, or maybe there's 1. If I try to go down by 2 again, I'd wind up with -1, which doesn't make sense as far as counting the number of zeros. So I'd stop there. Now, how do I figure out the possible number of negative zeros? Well, what I do is I take my original function, plug in negative x, and then I count the sign changes on that new guy. So again, since all I care about is the sign changes, I don't really care about the numbers, I'm just going to inspect this and do this up here. So if I plug in negative x, that stays positive. This right here, a negative to an odd power would become negative. A negative to an even power would become positive, but then I've got minus 26, so that's a minus. I plug in negative x here, I get a minus, and then at the end I had minus 315. So if you look at this, there's one sign change. It's from the positive x fourth to the negative 2x cubed. And again, this is me counting the sign changes in f of negative x, or p of negative x. So since there's one sign change, that means the maximum number of negative zeros is 1. And then I could go down by 2's, but I get stuck, right? If I try to go down again, then it would be a negative 1, which makes no sense. Finally, I can get an approximation for the number of imaginary zeros I have. And the way that works is it's the degree of my polynomial n. I'll write the formula. It's n minus p plus q, where n is the degree of my polynomial, so 4. P is the maximum number of positive zeros I have, which is 3. And q is the maximum number of negative zeros I have, which was 1. And so I wind up with 4 minus 3 plus 1, which is 4 minus 4, which is 0. But the weird thing is for the imaginary part of this theorem, this gives you a minimum number. So then I would count up by 2 instead of down by 2. So 0, 2, and 4. And I'm going to stop at 4 because 4 is the degree of my polynomial. Okay, so now that I've used that to know how many possible types of zeros there are, notice I'm guaranteed to have a negative 0. That's going to be there. Now granted, I'm also guaranteed to have a positive 0. That's going to be there. I have either 3 or 1. In fact, actually looking at that, I'm going to start dividing by positive zeros because I'm guaranteed to have one of each, but I could have 3 positive zeros. So I'm more likely to hit 1 if I start here. Again, doesn't really matter, made the list smaller, so you could just sit here and go through it. I'd like to save time, and besides, it's helpful to know these theorems and practice them anyway. So now that I've done this, I'm going to pick some positive zeros and do synthetic division. I'm just going to pick 5 and see what happens. So 5, and I'm going to divide that into my polynomial. So 1, 2, negative 26, 18, negative 315. Bring down the 1. 1 times 5 is 5. Add those, I get 7. 7 times 5 is 35. 35 minus 26, that's going to give me 9. 5 times 9, that's 45. Add that to 18. I get 63. And then 63 times 5, lo and behold, it is 315. So when I add those, I get a remainder of 0. So, woo, I found one of my zeros. It's 5. So that means, don't forget this factor of 3 here. And let me make myself some room. So factoring this out, I've got 3 times x minus 5, because that's a 0 that I found. And then I've also got, I had an x to the 4th polynomial, so this new one's going to drop down to x cubed plus 7x squared plus 9x plus 63. All right, so we found one of the real zeros. In fact, we found one of them. So now that I have that, I've got this formula right here, x cubed plus 7x squared plus 9x plus 63. And I need to go through and find the zeros of that. So, make myself some room here. Okay. Now I have a few options here. First of all, I found that 5 is in here, so I'll sort of circle that and check mark it. Notice 63. I could look at this polynomial on itself, x cubed plus 7x squared plus 9x plus 63. And if I list out the factors of that, I'm going to get the same factors. I'm going to get a 9 would go into here. I'm going to get a 3 and a 7. I will not get a 5, I believe. Let me double check that. Yeah, 63 is not divisible by 5. So therefore, I know I'm not going to have 5 again, and I know I'm not going to have negative 5. However, it is divisible by 7. Wait. No, it's not. Oh, yes, it is. Typed in the wrong number. Woohoo. So yes, so 63 is divisible by 7. So I could do positive 7 or negative 7. Let's do negative 7. Why not? So negative 7 goes into this. Let's go 1, 7, 9, 63. Bring down the 1. 1 times negative 7 is negative 7. Add those, I get 0. Multiply that by that, I get 0. Bring down the 9. 9 times negative 7 is negative 63. Dun, dun, dun. Remainder is 0. So now, this polynomial becomes, leave everything else here, 3, x minus 5. X, so minus a negative 7 becomes x plus 7. And then what's left right here, I had x cubed, so this is going to drop down to x squared. There is no x term, and then plus 9. So usually you'd stop there because let's look at x squared plus 9. Note that you wouldn't just know right off the top of your head that you're going to stop there. I'm looking at x squared plus 9 and I'm going, okay, let's look at what we have so far from Descartes' rule of signs. Let's look at this. We were told that we either have 3 or 1 positive zeros, so we found one of them. We found one of the negative zeros. So actually, I could have totally removed all of these now that I found that, because there's only one negative 0. Now, look at my minimum number of imaginary zeros. We're told it's either 0, 2, or 4. We've already found a positive 0 and a negative 0. So there couldn't be 4 imaginaries because there's only 2 zeros left over. And now if you look at x squared plus 9, notice that's a sum of squares. Any number that you square will be positive, and so a positive plus 9, you're never going to be able to make that 0. However, if you have imaginary numbers, the way they work is that when you square them, you get negatives. So let's look at this. Let's just take the x squared plus 9 and just plain old set that equal to 0 and solve. If I subtract 9 from both sides, I get x squared equals negative 9. I square root both sides, I get x equals plus or minus the square root of negative 9. Now the way imaginary numbers work is that when you've got square root of negative, you convert that to I. So you get plus or minus the square root of 9i, and the square root of 9 is 3. So we get plus or minus 3i. So those are my other two zeros, x minus 3i and x plus 3i. And again, look here. We've got 1 negative 0, 1 positive 0, and 2 imaginary zeros. However, unless you're explicitly told to give the imaginary zeros, factoring of a polynomial usually stops right here. Factoring this into the imaginaries is just done to demonstrate that they do exist and that they are given by Descartes' rule of signs. Whew, so that was a long problem. Just a quick little debrief. We had this polynomial right here. We factored out a 3 before we got started. We did the rational roots theorem, the P over Q, which gave us this really long list of different numbers to try. And it'd be really nice to have fewer numbers that I could choose from. So then I used the boundedness theorem. I just picked a number. I started with negative 9, and I did division. When I did that synthetically, using synthetic division, I had alternating signs. That told me that this was the lower bound. There were no zeros smaller than negative 9. So then I was able to cross all these out, including the negative 9, since it didn't divide evenly. I didn't get a remainder of 0. Then I used boundedness theorem again, but with positive 9. I did that division. Bottom row of its synthetic division, they were all non-negative. That tells me that 9 was the upper bound. There was no number larger than that. So then cross those out, and also 9 didn't go in, so it wasn't a factor either. So that shrinked my list a lot. So I just had negative 7 through 7 for my list of options. Then I used Descartes' rule of signs to investigate the sign changes and tell how many zeros I should have. So when I counted the number of sign changes in the original, I had 3. We go down by 2, so it would be either 3 or 1 positive zeros. Then you plug in negative x and you count the sign changes on that. So that came out to be just one sign change. So there is one negative 0 in the solutions. And then we can count the minimum number of imaginary zeros by n minus p plus q, which came out to be 4 minus 3 plus 1. And then that goes 0 for your minimum. And then you could have 2 more up until 4, because that's the degree of the polynomial. And then finally, with all that information, I just picked, who did I pick? I picked 5, and I did synthetic division. I went through that. That went in. So I rewrote my polynomial as 3 times x minus 5, because I have a 0 of 5, with my remaining polynomial of x cubed plus 7x squared plus 9x plus 63. Then on that, I just looked at it, and I noticed that 63 is not divisible by 5, so I could remove this as a possible factor. And then I chose negative 7 to go into 63. I did that. It worked. So now I had 3 times x minus 7 times x minus negative 7, which is x plus 7. And then I was left over with x squared plus 9, which, looking at that, I recognized is that's going to have imaginary solutions. Also, I know by this point that I don't have 4 imaginary solutions, so I have either none or 2 of them. And sure enough, 2 imaginary solutions were there. So that is how, if you're given a really long polynomial with large numbers that gives you this really long list, it can be very helpful to use a boundedness theorem to shrink what things to try. And then you can use Descartes' rule of signs to sort of give you an idea or an intuition of what numbers to try first, what ones might be the most likely for you to succeed in trying. And that was factoring this polynomial.